computer. Okay, so can somebody talk to me again?
Okay, how about now?
Yes, I can still hear you. Great. All right. There must have been something going on in the background because whenever I hit record, all the voices would go beep, 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 beep. You know, it's like, okay, that's not very helpful. But anyway. All right, so here we are with our participants, only 4 of us, but we will go ahead and get started. So for this week, we had planned, we were going to do Chapter 4, Carbon-13 NMR. And so we're going to continue on with Carbon-13 NMR and our kind of use the data we have from proton carbon and our depth experiments to get to elucidating really complex structures that we can't normally figure out. Then on Monday of next week, I was actually going to start 2D NMR so that I could creep in to having our UV vis added in somewhere there. But I'm going to start with 2D NMR because we have several different techniques available to us. And I want to talk about them individually because there's a het core, which is just carbon, 2 different types of atoms that we can look for correlation, but then there's correlation within each atom set as well. And then there's a couple other techniques I'd like to introduce as well. So I'm going to do that. And so I'm going to change that a little bit as far as our schedule. I should have the homework for our chapter here emailed out today so that you can start doing that. I won't be due until next week. So we're doing well there. I think I have posted all of the keys so far except for, I posted all the keys. So, and that's in the wrong place. Oh no, that's the exam. Okay, there we go. I'm gonna remove that, delete. Okay, so I've posted all the keys so far except for the homework, which I'm still grading, I'm sorry. All right, so let's pull up our slides for today. And I intentionally don't look at the answer to these things until after the class because I don't want to lead you down a road. I want us to actually discover as we go. So I did actually figure out that meta material was ortho, and I did send you out, you know, the spectrum showing you that was it. But I did able to verify that last one was the salicylamide. It's the amide of a salicylic acid. So, okay, so for today's, we're going to do kind of the same thing, and I'm going to add one little addition to it. Okay, so I want to remind you that when we do a depth experiment, the different angles mean different things. So in the 130, we have where odds are up, evens are down, and the quaternaries don't matter. Okay, to take a line from whose line it is anyway. Anyway, so then at 90 degrees, it's only CH's up, which means you can differentiate between CH and CH3s. And at 45, it's only things that are protonated. Okay, so that you can actually eliminate things that aren't protonated from that. And so that they each give us kind of a little bit of a clue on what's happening when. Okay, so let's first look at this next one here, and I'm giving us our empirical formula of C10H16O. And looking at this proton NMR, you would run screaming from the room if this is our first proton NMR we already saw. You can't tell the splitting, everything's kind of bunched together, it's got weird integrations. But, you know, just from what we see here, it looks like, I need a different one with a stylus there.
It's aliphatic alkane, sort of?
Yeah, it's definitely some kind of aliphatic alkane. And there's nothing much above here. So even though it has an oxygen on it, it's probably not an alcohol. It's probably something else. We don't know which of these peaks here might be our solvent peak. So that's kind of weird as well. We probably don't have any double bonds. If we did a quick calculation of our index, it'd be 1. Right? So we have minus 10 is 2 plus 1 is 1. Because oxygen doesn't count. So, ooh, we might have a ring. Okay, so that's telling us something even different here. Or we have a carbonyl. Let's go look at the carbon NMR. Okay, so we don't have any ethers, we don't have any alcohols, because our proton NMR would have shown something, above 3 here, right here. So we don't have any alcohols or ethers. And the carbon NMR tells us we have a carbonyl. So that accounts for our hydrogen deficiency index and our lack of those things. So now our hydrogen deficiency index is taken care of. Now we're looking for a linear ketone. Can't be an ester, we don't have enough oxygens, can't be anything else. So it has to be a linear ketone of some sort. Okay. So if we look at the rest of the carbon NMR, we see that we have, first of all, we want to look at this. This is solvent right here. This is chloroform right at 77 ppm. And we're going to blow up the rest of this here. So impression-wise, I think the two highest ones here are probably carbons that are attached to the carbonyl, because they're shifted up the highest. So we have 2 of those. Then we have what might be 2 peaks here, another 1, 2, 3, 4, 5, 6, 7, 8, 9, and then our carbonyl is 10. So we actually have 10 carbons shown in our proton our carbon NMR. So we have all 10 carbons, assuming this is 2 peaks here. So we don't have symmetry. We have 10 different carbons, and the proton's also telling us we don't have symmetry here. So that's something very interesting to know. So we still can't quite figure it out. I mean, this looks like a methyl group. These all look like methyl groups here because of the integration and the fact that they're below 1. So we probably have 3 methyl groups, but we really can't tell the split very well on these. They might be split or they might not. So that gives us our first impression here. So we do have 10 carbons, which is what we're looking for. We want 16 hydrogens. Let's double check that real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. So that means that this is 1 to 1 to 1 to 1 to 1 to 3 to 3 to 3. That gives us a total of 16 hydrogens. So we have all of our hydrogens, all of our carbons. We know where our oxygen is. Let's figure out the structure, but we can't do that with just these shifts. Let's look at the depth experiment. Okay, blow up the depth experiment here. Okay, now this one's done in reverse, where the 0 is at the top here. And so notice that the carbonyl has been taken off. We knew that the carbonyl doesn't have protons on it, so we don't need to include it in our depth experiment. We understood it was our carbonyl based on just the shift. And so this is our solvent again, and it goes away when we do the depth experiment. So it looks like we have, let's look at, let's start over here. At our 0 here, we have a peak. We have at our 45, we still have this peak. At our 90, a lot of those peaks go away. What does 90 tell us?
CH?
CH, just one H?
Yes.
So the 90 degrees tells us CHs are up. So that means we have only 1 carbon has a CH on it. Okay. So it looks like one of these has a CH and the other one looks like it went away. Okay. Just because this looked double thick, and then it looks single thick here. And look, when we go to our 135, it actually shows up below. Which means if our odds are up in this, that means this is a CH2. This is a CH2, CH2, CH3, CH3. 1, 2, 3, 4, 3, 4, 5, 6, 7. So that's all of it. Okay. So we have, yeah, let me see. Yeah, thank you. All right, great. All right, so we have some structure here. We have one CH2 and then a couple CH3. So that's telling me that maybe we have a structure that has CH3, CH3, H on it there. Something like that. And if we had that, those CH3s would be split into, actually those would be the same CH3s, wouldn't they? So, but we have something with just we definitely have some splitting here. So those CH3s have to be different though. CH3 right here. Now, what we also want to look at is our two peaks here are quaternary, right? Because they don't have hydrogens on. So if we look at that, that means we have to have at least 2 quaternary carbons. And because where they are, they're probably close to the carbonyl. Notice they're the shifted highest up. They're at the 50 and the 60. So those two might be the ones that are next to the carbonyl. Okay. So that gives us a fragment that looks something like, let's see, a fragment which has this, and then quaternary carbons. Okay, now that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9 of our 10 carbons here. But that doesn't account for all of our CH3s and CH2s. We have 1, 2, 3 CH2s to deal with. And so that would give us, and at least one more carbon. So how can we account for that? I mean, it looks like we have 3 methyl groups that are, you know, spatially different. And we've already got our hydrogen deficiency taken care of, so we don't have a ring. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have one more carbon somewhere, and we have to get a CH2 somewhere. What if we did that, which would give us our 1CH.
Can you please check the hydrogen deficiency? Because 3 of us are getting 3.
You're getting 3? Okay. 1/2 of 8 is 8. So that's 2 plus 3. Oh, yeah, you're right. It's 3. So, okay, we have 1 for our carbonyl. So what does that make it? So that means we have a ring somewhere. That means we might have more than 1 ring. Ooh, that would account for a lot of things, right? So let's say we have a ring, and let's see, the most common ring that we're going to have maybe is a cyclohexane. which would give us a methyl group there, a methyl group there, a methyl group here. And then this would be our only CH. This would give us a CH2, 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 CH2. So that's our 3 CH2s. And then this is our 3 methyl groups here, which is our 3 methyl groups there. And then our 2 quaternary carbons would be there and there, and our carbonyl is here. Okay. So, but it looks like the 2 things that are closest to our ring are quaternary, not a CH. Our CH, oh, our CH is pretty close to, it's above 40, so it could be one of the ones next to the carbonyl. Okay. None of the, but there's also a CH2 that's possibly up there as well.
The hydrogen deficiency is 3. So the structure you have made is 1 ring and 1 carbonyl. So there should be 1 more unsaturation.
Another one. Okay. How many carbons do we have? 1, 2, 6, 7, 8, 9. We're still missing. And we're missing a quaternary carbon. So if we take out, so do we need another ring here maybe?
Why are we not considering the possibility of an alkene?
We don't have anything above 3 in our proton NMR, and our alkenes would show up here in our carbon NMR. So that's why I think we don't have an alkene. So, right, because our alkenes, they start at 60 and go to 85 or up to 100, 60 to 100. We don't have anything in that 60 to 100 range. The highest peak we have is right here, just below 60. So I'm thinking that is a quaternary carbon, because as you add hydrogens, you actually are closer to 0. The more hydrogens you remove, the more those aliphatic carbons move up to the upper end of the aliphatic carbon range, which is right around 50. So I think we have maybe another ring here somewhere. And well, we could have a bicyclo compound. That would put the 2 most quaternary carbons at the highest, which are closest to where it's going to be bound to the carbonyl. So if we had another, we need another carbon, CH2, CH2. So those would be 2 hydrogens. That would give us our quaternary carbon. So we have 2 quaternary carbons up at the highest level. This now turns into a CH because we have that. Okay. And so we have a 1, 2, 3, 4, 5 membered ring, a 1, 2, 3, 4, 5 membered ring. We have a total of 6. We have a total deficiency of 3. We have a carbonyl, and let's see, we have 1, 2, 3 CH2s, and they're all different. And we have 1, 2, 3 CH3s, they're all different, and they don't look split. And then we have 1 CH. So this is consistent with what we have. Now, if we had a mass spec, it would actually show us that we have if we had this bicyclo compound, because it was a cyclo compound, we'd have a very high parent ion peak because it would be there. So let me redraw this in a different configuration so that we can see what this would look like on its edge here. And So then it would have a carbonyl here, a methyl group here, and 2 methyl groups there. So that would be a 1,2,2 bicyclo heptene, heptone. Okay, what in this does not support this? Okay, look at our proton right here. We have a 1, 1, 1, 1, and then a 2, 3, 3, 3. Okay, that means that only one set of 2 of these is relatively equivalent. The rest of them are not. Okay, and so if we are locked in a ring, imagine that you have non-equivalent hydrogen here, hydrogen there, hydrogen there. We have exo and endo hydrogens here, and we have the only 2 that are identical are the ones here on top because they're out in space. This is being crowded by the methyl group in this hydrogen. These see the hydrogen here, but not there. These don't see the same configuration. So I think the bicyclo compound fits based on the integrations for each of the peaks, because these are carbons with CH2s on them, but we only have one CH2 that has equivalent hydrogens. The rest of them are shifted. So, and I think maybe we might actually have this one hydrogen should be closer to the carbonyl somewhere, but I'm not sure. All right, is there anything that we see that does not fit this? Okay. So without additional information, like maybe a 2D NMR experiment, this is about as good as we can get. Okay. Questions on that? All right, well, let's move on to the next one. All right. C9H13NO. So let's go ahead and do our hydrogen deficiency, which is, let's do it right this time, David. Sorry, me. Okay, so we have 9 minus 6.5 plus 1 minus 1 for the nitrogen, and the oxygen doesn't count. So, oh no, it's minus 1/2 for the nitrogen, that's right. So that gives us 9 minus 7 plus 1 is equal to, that's not right.
I think so. It's for nitrogen, it's plus 1/2.
Plus 1/2?
Yes.
Okay, so that's plus 1/2. All right, so that takes it to 6.
4.
So it takes it to 4. Okay, that's great. Okay, so with a 4 and with this peak here, what are you thinking? Yes, I agree with you. I think it's a benzene ring. So, and it has a specific substitution pattern probably. Based on the way it looks, I'm gonna think it's a para-substituted benzene. Okay, so let's get that fragment out in the open and figure out what we have left. Okay, so, okay, well, actually, let's look at the carbon real quick and see if that's still supported. Okay, so we have something around 77. Oh, that's chloroform. So this is chloroform, so we don't have to worry about that. And it looks like we have at least 1, 2, 3 types of carbon. Actually, that looks split there. So it looks like this could be the 6 carbons for the benzene hidden under here. And then from there, we have 1, 2, 3 unique carbons outside of that benzene. And notice they're fairly high. This is 70, so this is 65, this is 55, and this is 40. So they're pretty high. So that's something we need to look at. And if this is 4, that would be 1, 1, 1, 1, 2 for a total of 10 hydrogens. So that means that if that's 4, oh, maybe that's 5. If this is 5 and this is 3, 8, 9, 10, 11, 12. So we might be missing a hydrogen here somewhere because we can't have 6 on there. So let's pull this up again here. Oh, interesting. We have some kind of splitting for here, 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 and we have a broad peak here. So we could have a nitrogen or we could have an alcohol. So we might have something with a hydrogen on it. One of those nitrogens or oxygens might have a hydrogen on it. And so it might be exchanging out real quick. So we might not get an accurate proton NMR. Okay, so looks like we have 6 carbons here. We have 3 carbons there. We have a total of 9 carbons, so all our carbons are accounted for. And so let's try to figure out what's happening here. So we have a benzene ring. Okay, that's 6. And then we have something with an oxygen on it. Okay. It doesn't go up above here, so it probably isn't a carbonyl, but it might be an ether. Let's look here. We have 1, 2, 3 peaks between 3 and 4. Okay, so that means we have 3 different hydrogens that are next to an electronegative atom. Okay, because like the ones carbons and stuff next to benzene rings are going to be below 3, but these are going to be bonded somewhere near an oxygen or a nitrogen. So that's telling us a little bit of something too, right? So being it's NO, I'm thinking we have an NH2 somewhere. Okay, so that takes care of 1, 2, 3, 4, 5, 6 hydrogens, which leaves us 7 hydrogens left. We have 3 carbons and 7 hydrogens. So, and none of them look very aliphatic. So it looks like we have, so it doesn't look like any of these are bound to the same thing. So like we couldn't have a fragment like this because this methyl group would be way down here. So that's probably not that. And we don't have any more hydrogen deficiency, so we can't have a ring with a nitrogen on that. Let's see. And in our carbon, let's see. What does this tell us in the carbon? We have 1 peak out at around 127. Most of them are right around 130, but we have 1 up at 140. What would cause one of the carbons in a benzene to shift that much? So we look at our table. Let's see, something to shift on there. So if we look at aromatic substituents on, or substituents on aromatic rings, we'll see that benzene itself is going to be right around the 130, which is where we have it right there. If we have an electronic drawing group like a carbonyl on it, it's going to shift it up to 140. but we don't have a carbonyl. If we have a donating group like an alkoxy, it should set up to 160. So what would a benzene with an amine on it be? The cyano group would shift it down to 112. So we don't have an aniline in here, do we? So we don't have aniline here. Interesting. I thought we did. Okay. So I think this tells us that we do have some kind of para substitution. So we just have to figure out how to get those last 3 carbons and 7 hydrogens on our system where it's not forming something that is so this looks like 1, 1, 1, 1, 2. So it can't be entirely equal there. We have at least something has hydrogen on it. Either that or an OH has a hydrogen on it. Looks like all 3 of these are pretty close to something. What about we'd have 3, 2, 1, and 3. So that doesn't agree with this here. I want to put another ring in there because that would give us that differentiation, but we don't have enough hydrogens there. So we have C3, O, and H7 left over. Oh, interesting. So that would make those different because of hydrogen bonding. Yeah. So that make a 6-membered ring for hydrogen bonding. That would differentiate some a little bit. So 1, 1, 1, 1, 1. Just Anybody have any ideas? I'm kind of stumped on this one. I don't know where to go with this one. So, okay. Well, what I'll do, let's see. Do we have any other information? Do we have a depth experiment? No, we don't. So we have some kind of para substituted aniline. And that's all I can tell you right now. I'll go look it up and figure out what it is. All right, let's move on to the next one. Right here. Okay, so this is a little bit different. Looks like this might be a doublet here. Definitely broad here. This is probably acetone. And then kind of a really big split and something up around 4 and 3. So we definitely have hydrogens near oxygens.
Oxygen.
Yeah, could be an ether right there. We have a C4H10O, which gives us 451. So our hydrogen deficiency is 0. So we have a fully saturated system. So we have 4 minus 5 plus 1, and oxygen doesn't count. So that should equal to 0. So that gets us completely aliphatic. Okay. We have a total of 4 carbons. So let's look at the carbon NMR. Okay. And in carbon NMR, we have 3 carbons. Okay. So 3 carbons of 4 carbons. 3, okay, well, there might be 2 hidden here. So 2 are pretty similar to each other. Right here, that's would be where our 2 that look together. Then we have 1 way down field and 1 way up field. Okay, so this is probably a methyl group of some sort. Okay, this is probably something bonded next to an oxygen. And this is the things in between. Okay. So what does this tell us here? We have, it looks like 1, 2, 3, 2. That's 5, 6, 7, 8. That's not enough hydrogens. So 2, 3, 1, 2. Oh, so you know what that is? That makes this 4 hydrogens, 1 hydrogen, and 3 hydrogens. So that's 6, 7, 8, 9, 10. There we go. So that is telling us here we have hydrogens that are pretty similar. We have like a CH2 bridge here somewhere. Okay. And then this is telling us we have a something that's maybe not nearby, like something that's off here. So we have 1 hydrogen, and then a methyl group. No, that's too many carbons there. We only have 3 carbons. I mean 4 carbons. But we don't have a ring because we don't have hydrogen deficiency.
So we see the carbon NMR.
Mm-hmm.
So the range come between the 40 to 80. So they are showing for ether, or it might be alcohol.
Alcohol, okay. The
So
one
alcohol.
or the one here.
Yes.
It's
This is for ether and the down one for the alcohol.
okay. The 65
Yes, ether.
for an for an ether.
Alcohol.
An ether or alcohol.
Yes.
So this could be a slowly exchanging alcohol peak. So we have 1, 2, 3, 4, 5, 6. And we need another carbon. Oh, here we go. If we put another carbon in here. So let's start with an alcohol at one end. OH, there, 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 and then there and there. OH, H. because we don't have a ring. Oh, and this is 2 and this is 4, so we don't have like a methoxy group. So we don't have like an ether with just a methyl group on it. So we don't have that because we don't have the right splitting. This suggests we might have an alcohol here, but then we have a CH2, 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 and then a CH3, but the CH3 is split by a hydrogen. So that would be, so that right there would account for this peak, but not that peak. We can,
What if we have ether and alcohol both?
what, we have ether on both?
Ether and alcohol both.
Okay, well, all right, let's try that. So we'd have to have O, and then an alcohol somewhere. But we don't have an unsplit 3 protons. All right, we don't have an unsplit 3 protons. We don't have, like this is 2 and 2 and 2, so we don't have any place for this CH3 to be. Ooh, what if this has 2 OHs on it? What if we had some kind of and then that would give us 2 hydrogens, 2 hydrogens, 1 hydrogen, 2 hydrogens, and a 3rd hydrogen. So that could be, this could be the methyl group here. These 2 could be this one here, and then this quaternary one could be the one way over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, 2 oxygens, and 4 carbons. But this methyl group would be definitely split into a triplet. It's the furthest away. It looks like a doublet. So that means if that's a doublet, there can only be 1 hydrogen here. So that has to be a hydrogen here, and then the OH there, and then 1, 2, 3, OH here. That's what it has to be. All right, let's see if this is consistent. We have 3 that are here. We have 1 and 1. This right here would be split by that 1 hydrogen, but not split by this. This could also be an alcohol, and this could be that one here. So each of these, this is 2 alcohols here. So we just need a total of, let's see, we have 1, 2, 3. Oh, we have 1 more. That's where to go. All right. That helps us right here. Where'd it go? All right. That's it. I think we have definitely this fragment here. This fragment here is supported by the methyl group, CH3 here that's split to 2, the hydrogen here that could be this one here, and then the OH. So if we had 2 alcohols that were approximately equivalent, they would both be here. So I think our fragment is then CH2, CH2, OH. Okay, now, that being said, let's see if this fits our system here. All right, so how many different types of non-equivalent hydrogen carbons do we have? We have 1, We have 1 carbon, 2 carbons, 3 carbons, 4 carbons. They're all different. This carbon and this carbon are going to be most alike. So we actually want, so definitely, okay. That doesn't quite fit.
I had a close structure to what you're drawing right there. Could we maybe debate as to why it wouldn't be this one?
Sure.
Let me get the right photo there. It's the one in the square, if you can see.
Okay.
It looks pretty close to yours.
Yeah.
Kind of like a wishbone.
All right. Yeah. Let me draw his one and let's see if it fits our data.
It's probably wrong, but I just wanted to maybe compare and contrast as to why it would be wrong, if that's okay.
Okay. No. Yeah. Let's do it. It's got this fragment that I just drew in it. So let's see. 1, 2, 3. Okay. We have 1, 2. That's 1 too many carbons. So I didn't draw it right. This is 5 carbons.
Just put the 2 alcohols on those each ends, and then it goes down to 4 carbons.
And so we have 1 H here. We have a 2 and a 2. We have a 3. Then we have this can actually be 1. We have 1. So this would be this one here. This would be here and split twice.
Oh, I didn't even think about it that way.
It would be here and not exactly equivalent. And then these would be there. So the hydrogens fit. All right, let's look at the carbons now. How many unique carbons do we have here? Let's go with 1. Those are the same. This is 2. And then this would be 3, this methyl group there. This methyl group would be this one here. So this is the CH3. These are the 2 CH2s. And then this is, no, this is the, these 2 are the same, and they're the ones attached to the oxygen. So this is the one with the CH. Okay, and that is consistent as well. So, all right. So let's redraw this and identify all the peaks to make sure we're okay with this. But yeah, with so many signals here, I was like worried that we don't have symmetry, but it turns out we do. All right, so we have 1, 2, 3, 4, and a CH3 here, an OH, OH. We have 1, 2, 3, 4 carbons, where 1 and 3 are here, 2 is here, and 4 is there. We have type 3, we have 1 type of hydrogen here, a 2nd type of hydrogen here, a 3rd kind of hydrogen here, and a 4th kind here. So these would be 1, this would be 2, this would be 3, and this would be 4. Yeah, that's very consistent. Okay. Carbon 2 looks like 2 peaks in the CNMR. Is it possible to just be split? It could be, it could just be a broad line. And so we can't really tell it's split. We didn't do a depth experiment to see if one of them went away or not. It could just be one line. So the idea that we have, just the first blush would tell us we have 3 different kinds of carbon, I think is consistent with our structure here. Okay, there was a carbon 2 looks like 2 peaks in the NMR. Again, that could just be a broad peak. It just happened to be a little broader in the copying of it. But no, I think this is consistent. All right. Any questions on that one? Let's see what we got. We got time. Yeah. All right. All right. Let's actually, I'm going to skip to one with adept so we can get some experience on that. All right. So we have C10H7Br. Okay. So let's look at the proton NMR first. It starts at 7 and it ends at 8.1. So what do we have?
Substituted benzene.
Something, yeah, something absolutely has benzene in it. And it looks like we have, let's see, 1, 3, 3 for integration. So it looks like we have 7 protons. Okay. So yeah, that's consistent. All right, so let's go ahead and do our hydrogen deficiency index. We have 10 for our hydrogen. I'm sorry, 10 for carbon, minus, remember bromine counts as a hydrogen here, so 8, which is half, is 4, plus 1 is equal to 6, 7. 7. So that means we have at least 1 benzene ring right here and 4 additional carbons with 3 more hydrogen deficiencies. Did I get 7 right? Double check. Because bromine counts as a hydrogen, so that's 8, which is half right there, plus 1 is equal to 7. Okay, so first thing when you think of, I have 10 carbons, I have a hydrogen deficiency of 7. The first thing I would think of is this. Right here. Because that is going to give us a bunch of aromatic peaks. And it's going to give us, if we substitute any one of these with bromine, we're going to have 1, 2, 3, 4, 5, 6, 7 hydrogens. And we have a double fused ring, which is a naphthalene. Okay, good. Somebody else got 7. All right. Okay, so I'm thinking it's a naphthalene of some sort. And let's look at our, if it was naphthalene, right here, let's figure out how many different kinds of carbons we have. Okay, so assuming we have 1 bromine here, that's going to give us 1, 2, 3, 4, 5, 6, 7, 8. These might be the same right here. These might be the same carbons. These are going to be different because of where the bromine is. So I'm thinking we have at least 8 kinds of carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9. So they're not equal. So we have 10 kinds of carbon here, maybe. 1, 2, that looks like 2 peaks there. So we have 10 different kinds of carbon. So we don't have a symmetry element in it. Okay. So let's look at our proton here. We have 1, 3, and 3. So that means 1 is shifted up away from the others. And I bet it's that through space 1 there. And so for hydrogens, I think we have a 3 here, 3 here, and then the 1 here. No, that doesn't, yeah. We only have monobromo right there. So it's got to be, there's only 2 positions it can be in that are non-equivalent. Okay, so it can either be in this position or it can be in this position here. Otherwise, if you just flipped it over and rotated it, it can be in any of those other places. So it has to be the first carbon or the second carbon over in the benzene ring. So being with this 1 here, yeah, I think it's going to be this one right here. I think it's the that position here, which gives us the hydrogen here being unique out here, and then the rest of these just kind of blend together. because that looks like 1 and 2, 1 and 2. That's 2.
I'm a little confused. Like next to the bromine, the hydrogen next to the bromine on 3 carbon, isn't it will be same like the 1?
Oh, this one over here. Yeah.
Yes, 1 and the 3 are similar.
Yeah, I think you're right. Let's move it back to the other one and look for different types of hydrogen. So if we had bromine here, we're only going to have 1 hydrogen next to a bromine, which would account for that.
Yes.
We have 2 hydrogens here, which could be one of these peaks. Then we have 2 of these. This hydrogen might be a little different because of through space interaction, so that could be one of these peaks here. Then we have these, and then this actually has interaction with that hydrogen, so this would be our other. Yeah, I think you're right. I think you've convinced me. It's the bromine has to be in that one position where it's only influencing 1 hydrogen. And if it's only influencing 1 hydrogen, it's consistent with our proton NMR. Okay. Do we see how looking at the uniqueness of the 2 different possible isomers narrows it down to the 1 isomer? NMR is all about equivalency, right? And so if things are equivalent or close to equivalent, they're going to be very close together. And if they're not, then we'll see the difference when we do. So let's look at the depth here. Since we have a depth, okay, in this case here, we have everything has 1 proton on it except for 1, 2, 3 carbons. Okay, so those are quaternary carbons, and we have 1, 2, 3 of the quaternary carbons that are tetrasubstituted. So our depth experiment actually is consistent with this. And note 2 of them are really high, so this is probably the one with the bromine on it. This is probably the one next to the bromine, and then this is probably the one way over here on the other. All right, questions on that one?
Can you once again explain the different, the non-equivalent hydrogen and the equivalent hydrogen on this example?
Yes, let me redraw it right here. Yeah. Okay, so we have to think that the hydrogens here are actually fixed in space and are closer together than the other hydrogens out here. Notice that these 2 are actually close together because it's locked in that ring, right? And so the hydrogen, let me do, so the hydrogen next to the bromine here has 1 interaction. The hydrogen with a through space interaction to the next bromine is a different hydrogen, right? So I think these 2 are different hydrogens. I think that the hydrogens, these 2 hydrogens are going to be closer to the same. But I think that we could also say that these 2 hydrogens are equivalent. Those 2 hydrogens are similar, which leaves 1 hydrogen here, 1 hydrogen here. So we have unique hydrogen 1, unique hydrogen 2, unique hydrogen 3, and then a pair of hydrogens that are similar. So we should have 1, 2, 3, 4, 5 different signals. And if we go to our NMR here, we have 1 signal, 2 signals, that would be 3, because I'm calling this a 1 and a 2, 4, 5 signals. So 1, 2, 3, 4, and 5. So we have a 2, 1, 2, 1, 1. 2, 2, 1, 1, 1. Okay, did you follow that one? So if I,
Yes, thank you.
so we have the number of equivalencies if the bromine is in that position works out correctly. Okay. All right, let's try to figure one more out before our time is up here. Okay. Let's see, that's okay, let's try that one. That one looks hard. Okay, so we have C5H8O. So we have 5 minus 4 plus 1 is equal to 0. Okay. So that gives us that. We have something way up here. And we have a total of 8 hydrogens. So it looks like maybe 2, 2, 2, 1, 1. Okay. None of them are quite broad enough to look like an alcohol peak, but that one looks like a triplet maybe. Can't really tell. All right, let's go to the carbon NMR. Wow, we have something way up here. We have something at 100. This is chloroform. 2, 3, 4. So we have 5 carbons present and they're all different, so we don't have symmetry. We have 1 oxygen and we have 8 hydrogens. Okay. And we don't have any methyl groups. So what do we have? We don't have a hydrogen deficiency. So we have to have something.
Marvin's actually right. The deficiency index is 2.
Oh, okay. It's 2. All right, that makes it easier. Okay. With 2, that makes it a little easier because that means we could probably have a ring. So if we had a ring, oh, that might account for this here too. One, 2, 3, 4, 5, 6. Oh, we need another carbon. And so let's start with this here as our structure. We have 1, 2, 3, 4, 5, 6. Membered ring. With an oxygen in the ring and a double bond here. Okay, first of all, that gives us 1, 2, 3, 4, 5 unique carbons. This would be the alkene carbon right here. And then this would be the carbon next to the oxygen there. This would be the CH2 next to an oxygen. And then this would be the 2 CH2s that are farthest away. And these would be the 2 alkene hydrogens. And we each have 1 hydrogen in them. And then a CH2 next to an oxygen, and then CH2s away from the oxygen. So let's see. This would be carbon 1, carbon 2, carbon 3. I'm sorry, carbon 2, carbon 3, carbon 4, carbon 5. I would call this carbon 1 because of the alkene plus the alcohol. carbon 2 for the alkene, carbons 3 and 4 because they're the farthest away from oxygen, and this makes this carbon 5. And let's look at the hydrogens here. Hydrogen type 1, hydrogen type 2, 3, 4, and 5. This would be hydrogen 1, hydrogen 2, hydrogen 5, and then this would be 3 and 4. This one's slightly higher because it's closer to the double bond. This one's only got CH2s on either side of it, so it's going to be the lowest one. Okay. Questions on that one? And notice we don't have symmetry here because if we put the double bond somewhere else, we wouldn't have this really high shift here, okay? And so we wouldn't have this high shift here. So the double bond has to be next to the oxygen because of those shifts. So that eliminates the other isomer possible. All right, let's see. Any questions on that one? All right, let's do one last one, and maybe I'll get the hydrogen deficiency calculation correct. All right, let's start with this one, C6H10.
Sorry, can you just explain the point where you find that it's a heterocyclic compound?
Well, we have a hydrogen deficiency of 2.
Yes.
We have symmetry, and it looked like we had, based on these peaks here, it looks like we had 2 different hydrogens next to where an oxygen was bonded to it.
Oxygen, yes. Okay.
And in the carbon right here, we have only one CH2 that has in the zone where it would have a carbon, an oxygen bonded to it. Then the others have to be alkene.
Double bond. Yes.
One of them shifted way high, so that had to be something else bonding to it. And then these look just like alkanes down here. So that's what gave me the hydrogen deficiency, and the lack of symmetry told me it was probably a ring, and an unsymmetrical ring at that. The other thing that told me I had a ring here is the fact that none of these right here integrated to 3, okay? Meaning we don't have a methyl group anymore. So we don't have a straight chain because we don't have a methyl group.
So that's your indicator for knowing that you're in a ring structure, or that CH2s or CHs are actually apparent instead of the methyl. If you don't see that methyl group, that's where you know you're going.
If I don't see a methyl group, I try to see if a ring fits first, yes.
Beautiful.
Yeah, because, you know, if you have like a nice singlet with 3 hydrogens at like 2.5, start with a methyl ketone. If you know, or if you have a nice if you have a nice like something right at 1 ppm that has a nice triplet with 3 protons, that's the methyl at the end of a chain. So you should start seeing that certain things pop up again and again and again, and those weren't here. So that was telling me ring.
Yes. Okay. Thank you.
So let's look.
I'm a little confused about the integration. Is there any particular way to know that it is 3 and it is 4, it is 1? Like sometimes I'm confused with 4 and 5 and 3 to 4. They are very close.
What you can do for that is, because the height of the integration here is the same, you can just take like literally a piece of paper and took one of the peaks that looks like the smallest, and
Okay.
on that and say, okay, that's one of these units, and then this one's also one of these units, and this one's 2 of these units, 2 of these units. And so, or if you had a ruler.
Scale, yes, that's what I'm asking.
Yeah, ruler, or just because the absolute value is not important when we're looking at these. What you should be able to tell the difference between 1 and 2 and 3 just by that relative measure on the side of the piece of paper. Okay. So I do that a lot because like this one right here, again.
So one last question, sorry. Can you see the peak in the NMR around 2, proton NMR around 2? So there is an integration above that peaks, red, can you see the red dots above that 2 peaks? Yeah. So it's these looks like similar to me, to just like the 4.
Right.
These 3 are same.
So if I took something and measured that right there, I would think if I called this my unit, whatever it is, if I took that over here and then added another one to it, that looks like 2 of these units, right?
Yes.
And so if I just took this over here, that looks like that. And so that's going to be 2 of those. And then that would be 2 of those as well. So that's all I'm doing, is just doing a rough estimate of, well, it's more than, it looks about twice. Because if we do this one as our integration over here and just pulled it over here, it looks like half above and half below. So this is twice as big as this over here.
So it's mean the peaks at 4 and the 2, they are same number of proton.
I think that these have the same number of protons as these 2. Yeah. So
okay.
All 3 of these peaks have the same number of protons. And so that would be consistent with this structure being 2 protons, 2 protons, and 2 protons. And 1 proton and 1 proton. So, you know, drawing those lines all the way across, that's what it looks like to me. And again, it's a relative thing. When you're doing research, you want to get it exactly right, but in interpretation, you can use that rough estimate, and it usually works. Okay. Complicated structure. C6H10O. Okay. Yeah, the peaks themselves you don't look at, because the integration is completely the area under that curve. So if you have a slightly broader peak or narrower peak, it could change your integration significantly. Remember, every time you split something, it makes them look smaller and smaller and smaller. But the area under the curve is where the protons are. That's why we always use the integration, not the peak height. So let's see. 6 minus 5 plus 1 is equal to. Did I do it right this time? Okay. Half of 10 is 5, minus that plus 1 is 0.
No, it's 2.
It's 2. It's minus 1?
It's 6 plus 1, 7. 7 minus 5 is equal to 2.
So that's plus 1 plus 1. It's equal to 2. Okay, great. Thank you. I was going to have a hard time figuring out where that double bond came from if we had a hydrogen deficiency of that. So we have a hydrogen deficiency of 2. Okay, so that's great. And from the look of it, we have a double bond right here. And looking at that relative ratio of peaks here, I'm going to say a 1 to 2 to 2 to 2 to 2 to 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That matches the number of protons we have. Okay, so do we see where we got those integrations estimated that quickly? Okay, so that being said, we should look somewhere immediately. We should see that we must have a terminal alkene. Okay, because we have a 2, a 1 in the alkene range, which means we must have this right here is telling us we have this fragment right here. Okay, with something hooked onto it here. So we have one hydrogen here and the two other hydrogens here, and they're hooked to alkenes. Okay, so that fragment is really obvious there. Okay, this right here is telling me probably OH. Okay. Okay. Can't quite tell the splitting on these. They look like they might be split, but notice there's nothing with a 3, which means we don't have a methyl group. Okay. This looks like it's split into a triplet, so it looks like it's near something with 2 hydrogens on it, but we don't know. Okay, so just this so far, we've used up one of our saturations here, and it looks like we don't have any 3s here, which means we might have a ring. Okay, so let's look at our carbon NMR. In our carbon NMR, we have 1 at 60, so that's a carbon next to an oxygen. We have these down here, so those are carbons not next to an oxygen. And then we have 2 peaks up here, probably next to, those are the alkene. Okay. So that being said, we have 1, 2, 3, 4, 5, 6, and possibly an oxygen OH. All right, so let's hook this together then. So we have 2, 2, 2, and so a 2, 2, 2 pattern probably looks something like a chain with something at 2 ends, so 2 different things, 1 at each end, right? Because that would give us a 2, 2, 2 pattern. And if this one was at this end and had an OH here, that would be consistent with all 4 of these peaks give us a 2, 2, 2 OH peak. Okay, and it also agrees with this. This carbon would be this one here. These 2 carbons would be these down here. Okay, so this is a pattern that happens a lot. You have not a terminal methyl, but a terminal alcohol. And it gives us this pattern of 2 hydrogens, 2 hydrogens, 2 hydrogens, and then something else is attached. Okay, so if we look at this, we had 6 carbons, and we have 1, 2, 3 of the carbons accounted for. Okay, but we only have 2 more carbons for our terminal alkene. So we have to have something else here. There has to be somewhere else for our deficiency. Okay, we don't have any carbonyls because it doesn't come up here. We only have 1, 2, 3, 4, 5 types of hydrocarbons, but we have 6 carbons here. Okay. So what are we thinking here? 2, 2, 2. So we definitely have this fragment here. How do we get those other parts there with our deficiency? One, 2, 3, 4, 5 carbons, but we have 6 carbons. We have a double bond here. So we'd have to have a carbon that was the same. And we have the hydrogen. 2 alkenes. They would have to be kind of linked together then. So let's see, that would give us this would be 1, 2, 3, 1, 2, 1, 2, 3, 4, 5, 6 OH. So that would give us 1, 2, 3, 4, 5 alkene hydrogens, 1 aliphatic hydrogen, and 1 next to the OH. What's the other way for us to get out of a hydrogen deficiency problem? A ring. So let's try a ring. We have to have a ring, we have to have an extra carbon, but we have to have some kind of symmetry element in it. Okay, so let's see with this right here. We definitely have a terminal alkene because of this. So that takes away 2 of them, which gives us 4 carbons available for the ring. 1, 2, 3, 4. Right here. So that's 1, 2, 3. And then that would give us 1, 2.
Why not the 6-member ring with 1 unsaturation and OH on the next carbon? Yes.
Okay. So that would give us our 2, 2, 2, but 1, 1, and there. We only have 1, 2, 3.
There's one more hydrogen, like the OH. Yes, yes.
Oh, and that would be hidden under this peak, wouldn't it? Because it's being shifted up by the OH, but then it's being shifted over by the alkene. So it's actually hidden under this peak. But let's see how many different types of carbon we have now. We have 1 kind of carbon. Let's count them in blue here. 1, 2, 3, and then this is 4, and then maybe 5. 1, 2, 3, 4, 5. Let's see.
I think so. The hydrogen at carbon number 3, it's close to OH and alkene. So I think so. It's close to 6 in proton NMR.
This hydrogen right here.
Yes, this is around 6 in proton NMR because the integration is 1.
Okay. All right. Yeah, I could do that. And so that would account for the extra proton here. So that would account for the 2 of those, the 1 with the alcohol on it, and then these. So it means that, oh, then these 2 carbons are the same and this carbon is the same. So it's a total of 5 carbons. Okay, so let's look at that argument one more time. Let's redraw the structure and then label all the different hydrogens and look for consistency. All right. And then that will be it for today. All right, so let's go draw the structure here. And we have hydrogen, hydrogen, which could be these. We have this hydrogen here, which could be that. We have these hydrogens, which are going to be that. And then these hydrogens are probably going to be the furthest down, and then these would be next, right there. So that's where our hydrogens would be. For our carbons, we have 1 and 2. Those are going to be 1 and 2. Probably, actually, yeah, this is going to be 1 and this is going to be 2 because it's furthest up. So this is 1 and 2. This is definitely 3 here. And then we probably have an equivalency of maybe these 2 are the same here. And then this last one is the one next to the alkene there. So that's a maybe, yeah, that fits. Okay, so whenever you end up coming up with your structure, go back and make sure it fits your data. Don't just say, oh, I think I saw it. So We have a structure that's consistent with all our data. We can identify which hydrogens are where in the spectrum, and we can support that with where our relative shifts should be in our NMR, in our books here. In fact, I believe that structure is in our proton NMR area, and we can see how close we got to the structure there. There are certain alkenes that are already in that proton NMR chapter. I think this might be one of them. No, it's not. All right. But it is consistent, so 5 and 5.9. Yeah. Yeah, the carbon next to that is going to be shifted up to the 5.9. All right. So it's not easy, but it's really important that we make sure we go back and redo it. All right, I'm going to go ahead and stop recording since we're pushing up on time right now. If you have to run off and go to class, please do. And if you don't, you can stay behind